Okay, so let's start this presentation. My name is Thomas Barbosch, and I'm presenting to you a joint work which I did with Maxime Villiard. It's called KLEAK. It's practical kernel memory disclosure detection. But before going into the details, and I may warn you, this is a little bit more technical than the last talks. We have to do a quick recap on 2 or 3 things. So the first thing is actually what is the syscall? And well, I suppose everybody knows there's user space, kernel space, and user space. We've got potentially untrusted programs, and they're kind of isolated. And then there's kernel space where the kernel is running, and there's where the power lies. So the programs are isolated, and to do anything meaningful, they have to ask the kernel to do so. So they use syscalls, like for example syscall X, which could be send a packet or write to file, and then you call it to the kernel. There's a syscall dispatcher which does additional preparation, chooses the right syscall to call, and finally return to the user program. And the interesting thing which I'm talking about now or later will be this boundary between user space and kernel space. There's a trust boundary. Programs should not read stuff from kernel which they're not allowed to read, and they shouldn't write there. So there's some data exchange usually going on. So first, some data has to go into the kernel. This means the user program cannot write directly into the kernel space. So what it's going to do is user program provides pointer to buffer, and then the kernel fetches this data and works actually on this copy. Here in the slide, you can see there's some buffer on a user space stack, and it gets copied into the kernel stack, and some work is done. And again, there's this trust boundary between user space and kernel space. And now the really interesting thing, which is this talk all about, it's about copy out, getting data out safely and securely out of kernel space. And typically, there are also dedicated functions like copy out string, in order to get this data to the user mode program. And the kernel does not typically write directly into user space. It uses these APIs also because stuff like supervisor and mode access prevention. So, and it's kind of an exploit mitigation. So, and if you know what is a syscall and you know about this trust boundary, then you can follow this talk perfectly, I suppose. So it's about kernel memory disclosures. And what are they? Well, one could say they are inadvertently writing data from kernel to user space. So data that actually does not belong there, but which was written there by accident. And as a consequence, well, first you may leak random data, but for an attacker that's useless. But then the interesting stuff can happen. For example, you may leak kernel pointers or parts of a kernel pointer. And if you've got like kernel ASLR, then this breaks basically your exploit mitigation. So, and also it can happen that you write more sensitive stuff, maybe crypto material, and so on and so forth. Typically, those bugs do not lead directly to an exploitation or a privilege escalation, but they are on modern system that they've got kernel ASLR. They are a step towards this goal. So in order to do some privilege escalation, you have to know where the kernel lies in memory, and you need to get kernel pointers and so on and so forth. So let's have a quick look how such a kernel memory disclosure looks in code. I hope everyone can read this. This is a kernel memory disclosure that I found by auditing the FreeBSD code. And on the left-hand side, we can see actually the code of the syscall. It's called a syscall get context, which provides the context, the register states to the user space program. And it's architecture dependent because on different architectures you got different registers and stuff like that. And on the right-hand side, that's the kernel stack. We're going to call into it. There's a little pointer, and now we're at the beginning of this syscall. And what happens? We're pushing the parameters out on the stack and the return to us. And still most of the stack is initialized. We don't know what's actually laying there. And now there are variables, and they're only reserved at this point in time. So the stack gets opened for the U context, and also somewhere logically there should be the return value. And there's some sanity checking on the buffer, and then you go into another function which is architecture dependent in this case, and which is called getMContext, which fills this UC struct with the register states. So how does this struct actually look like? Well, it's a struct which is nested with structs. I think on another layer it's also nested. So it's kind of complicated. Nobody really knows how this will be laid out into the memory by the compiler because of padding and stuff like that. So I believe nobody here in the room will get it right. So we don't know what happens usually with this stuff. So, and as a consequence, this function mGetContext fills this memory area where we pass the pointer, and then there's some hole. And now we're copying the whole struct to user space again. And this whole by now is the leaked stack memory. So everything that was before now is in user space. And in this case that was 2.5 kernel pointers that were passed, like 20 bytes every time. And that's the thing with there. Like you won't see it at the first look maybe, but then if there was in FreeBSD kernel ASLR, it would have been broken. So the fix here is quite easy. Well, you just zero out everything before you write to it. So why are they hard to detect, those kernel memory disclosures? Well, there are silent bugs, so they do not yield crashes. Without a crash, nobody usually will look into it. So maybe these are also hidden behind your C library, because you usually don't talk directly with the kernel via system call in your userland program, and maybe you won't get the leaked bytes through your C library, and nobody will notice. The root of all evil here in the end is the C programming language, and there's no, let's say, safe way to transfer data from kernel to across trust boundaries. Also, the current state of compilers doesn't help. I mean, they tell you if there's a non-initialized variable, but then they fail if there's a nested structs of structs and stuff like that, and they don't give you a hint that there may be a kernel memory disclosure. System memory allocators, they're also a reason, because usually the kernel stack is not zeroed out, it's uninitialized. The heap returns in many cases uninitialized memory that could be leaked to the userland. Furthermore, architectures are also a thing here, because on some architecture actually the code will leak, on the others not. This is because compilers may add padding and so on and so forth in the structs, and you won't notice this. If you develop something on x86, it may leak on AMD64. So, and maybe some developers are not that aware of this issue, are not taking seriously, but yeah. Typical error sources, there's a paper by Euro project, Google Project Zero, and it's like 20 pages just about typical problems of kernel memory disclosures, and this paper came out like half a year ago in summer 2018. So everybody who's working on low-level stuff, I can definitely recommend and read it, and then afterwards you will know a lot about this kind of bug class. But in general, it boils down to stuff in the C language again. So in uninitialized variables, well, the compiler will warn you at least here. But then you've got struct alignment stuff. So stuff gets aligned so that you can fetch it in one CPU cycle by the compiler. There may be pegging bytes at the ends in structures. Unions are kind of evil as far as I know, because if there are two members, a smaller one and a bigger one, then the union will be the size of the bigger one, and if you copy out the smaller one to userland, there will be a padding at the end. And again, there's the allocator in stack won't help here. So how to avoid it? Basically, first, if you do the stuff general, passing data across trust boundary, it doesn't have to be userland, kernel land, can be also network, for example. So local variables on the stack are usually uninitialized. We don't know what's there. And your heap implementation, if you don't pass flags, for example, it will be uninitialized as well. So initialize it. Don't trust the compiler at the moment. I guess in a couple of years there will be some advancement, and they will help you more on this. And don't assume any certain architecture padding when laying out stuff mentally in in memory. So this will break your neck. And yeah, initialize your data as soon as possible. In the case, for example, that I showed you, if you trust that it will happen later, most likely won't happen. So do it yourself as soon as possible, and you won't forget it. Again, if you're writing your own syscalls, then well, dump the stuff you're exchanging in userland and look for some bytes. That would be another way to find this leaked bytes. And finally, when in doubt, zero out, because security of efficiency. And when you go the long way to implement kernel ASLR, then well, one leaked byte may be enough to break it. So this couple of cycles for zeroing out data structures may help you a lot there. So what to expect actually? If you look at the history of kernel memory disclosures in other operating systems, that's not a BSD problem. That's a problem everybody's facing at the moment. Like in a publication of Lu in 2011, I think, they stated there were around 40 kernel memory disclosures detected mostly by manual code audits in the Linux kernel, and they automated stuff and found like 20 more in Android and Linux. Then there was this paper of Euro last year who found around 70 alone in Windows. So everybody's fighting with this thing, and the list goes on. There are many individual researchers that found kernel memory disclosures by having a look at the code. So far there hasn't been any a systematic investigation in the BSDs, as far as I know. Maybe you can say an exception would be OpenBSD manual code reviews. But then again, correct me if I'm wrong, but I think 2 weeks ago there was an Everton notice in OpenBSD about the pledge syscall, and there was a kernel memory disclosure. So if this is true, then everybody's fighting with this. So the assumption is that there must be many kernel memory disclosures in the BSD. And while I was reviewing the code of FreeBSD, NetBSD, OpenBSD, I proved it by finding some low-hanging fruits. And then I thought, well, we could actually patch the kernel and use some form of time tracking and do this automatically. And this is basically where I teamed up with Maxime, and we came up with this idea that's called KLEAK. So KLEAK is an automatic approach to detect those kernel memory disclosures, and it uses a rudimentary form of taint tracking. So we taint our memory sources like the kernel and the stack. Then we let the bytes, the tainted bytes, travel through the kernel space, and at some data sinks, in our case copy out string, we look at the buffers and search for certain marker bytes if they're there. And if they're there, then we detected such a leak. So let's have a quick look how this actually works. So we've got our program, we've got our potentially uninitialized stack here, and we've got our patched heap that already returns tainted pages. And if we use a syscall and call into the kernel, at the syscall dispatcher, we taint the whole stack by calling a function of our own that allocates a huge array and mem sets it with our marker byte, and then we call into the system call, and the syscall will actually do memory allocations, and it will get stuff from the heap. It will get it will write to the stack, and then at some point there must be some exchange, so data gets copied out to the user space. So that would happen here, copy out to user space, and this is basically our data sink, where we have a wrapper around copy out, and we look at each buffer and check, well, is there a marker byte? Like if there are 4 of them in a row, then we know, cool, there's a memory kernel memory disclosure. You may think, well, 1 marker byte, that's not a good idea, because however uncommon a byte may be, you will see the bytes all the time. So if you think about system calls like get_random, all 255 values will be seen there. So therefore, we had this idea of a heat map where we introduce rounds. So we rotate the marker bytes. In the first round, we've got marker byte 1. In the second round, we've got marker byte 2. And every time we encounter this marker byte in copy out, we notate this, we write this down into our heap map. And for example, if we say we want to check for 8 rounds for the leak, then we encode it in the heap map, 8 rounds, and this decreases the possibility of false positives tremendously, because it's very improbable that our marker bytes will be at the same offset all the time in a random function. So there still might be false positive, but it should decrease it tremendously. So let's go into, and then again you return to user space. Let's go into the details. So we've got our data sources. That's one source is the heap, and well, we instrument basically the dynamic memory allocator to return our marked chunks. So we memset the chunks before we return them. If you call malloc, for example, we return you the memory you requested, but memset with our marker byte and not like uninitialized. So the exception is, well, 0 chunks. If you request 0 chunks, we have to return 0 chunks, because if we don't, you get kernel panics. Then another source is the stack. So right before entering the syscall, actually, at the syscall dispatching, we call our own function that taints the whole stack. But then we've got a problem. During execution of the syscall, you enter into another function and another function, and those will open a local stack, will close it, there will be some data, and maybe the leak will be a little bit deeper in the syscall. So what we do is we continuously retaint the stack. So we use some compiler instrumentation, and every now and then we retained a smaller part. I think at the moment it's 512 bytes. We retained it, and this increases our probability to encounter those tainted bytes later in the copy out. And then detecting those leaks, it's like a very rudimentary taint tracking, so we don't track each and every byte through the kernel. We let them travel, and at the source, which are defined as copy out and copy out strings, at the strings, excuse me, we check on each invocation if we see those marker values. Now you may ask, what are good values for marker values? So if I would mark my tainted chunks, heap chunks, for example, with 0 or 255, this is not a good choice, because those values are probably are more likely to occur. And we had this idea, well, we at least try to estimate the byte frequency first and see what happens, like what bytes are more common than other bytes. That's not super scientific exact, but for our case, I think it was a cool approximation. What we did was we patched copy out and copy out string in NetBSD 8, and every time copy out or copy out string was called, we had an internal data structure, and we counted the bytes that we saw in the buffer to be copied into user space. So we counted in this buffer there were 3 times the byte 1, 2 times the byte 2, and so on and so forth. And then we added another system call in order to fetch this data from kernel space and read it out. In order to get a lot of interaction with the operating system kernel, we used the test suite of NetBSD tests, ATF, and this, I think it ran in my VM half an hour, something like that, and it provoked many invocations of copy out and copy out string, and that's basically the result. So on the left hand side, on logarithmic scale, you see the results of copy out, and on the right hand side you see the results of copy out string. So first you will notice on the left hand side the bytes like 0, 1 that are a little bit more common. Then in the middle, that seems to be the same as the ASCII spectrum over there, more or less. So those seem to be common. And then at the end, there are also like bytes like -1, which is 255, is quite a common byte. But bytes at the end of the spectrum, like in a range of 200, 220, not that common. So maybe choosing them as marker byte would be a better idea. Then on the right hand side we see the values for copy out string, and this copies out only ASCII strings. So the good news is we did not account like a byte at 200, which would be something like kernel memory disclosures. The bytes are actually in the ASCII range, and there's 10 and this little spike at the left side, that's like line feed, and that's value 10 or 11. So on the bottom you can see on the left hand side the bytes that are quite common, like 0, 255, I don't know why 1797, but and on the right hand side those are the bytes that are not so frequent and which we choose as our marker bytes, and it's like 154, 218 bytes like those, and I think of those 10, like 4 maybe are prime numbers. So our solution, as I told you, using only one marker byte, it's not a good idea because you have a considerable amount of false positives, and the solution was basically to invoke the kernel entry points over and over again, but changing the marker points, the marker bytes, and using this hit map. And with this hit map, each offset we had a byte, and each byte contains 8 bits. And if we choose 8 rounds, we switch on each round. If we encounter a byte, we switch a bit on, and in the end, we jump the results. So this can be done in the implementation in NetBSD with the userland tool KLEAK, which interacts with the kernel part. In general, it's not enabled by default, it's a developer option, but it's your system remains quite usable, so it's not a tremendous slowdown that's happening if you use KLEAK. And here we can see an example. We call KLEAK with the number of rounds, in this case 4, and the command PS. And what happens was that there came the output, and Maxime found this one, which was quite tremendous, which leaked 931 bytes of memory from userland to kernelland. So I think this was the biggest one that we found. So that's quite a lot. So quickly about the limitations. Well, one limitation is simplicity and speed over precision. So we are not that precise because we don't have this super sophisticated chain tracking where we track the bytes through every operation in the kernel. We rather let them travel through the kernel, check at the end, and that's it. So that's simple because the patch of KLEAK for NetBSD was definitely less than 1,000 lines. I don't know exactly how many it was, and it's kind of fast. You don't have you don't know tremendous slowdown, and that was one of our goals, and actually it worked, as you will see later on. So code coverage, it's a dynamic analysis approach. That's the problem with dynamic analysis. So we have to cover as much as possible. You can simulate user interaction. You can use, for example, you can use testing frameworks like ATF tests. You could use fuzzing to improve the coverage, but in the end, close to 100% coverage is difficult, but that's the problem of all the dynamic analysis approaches. Another thing, maybe portability across the BSD. It's not a huge issue. I did a proof of concept port to FreeBSD, which gave some results, and I think you can do it to Apple and to Linux if you want, and to Windows I don't know. So those are the direct results actually of KLEAK, and I think it's not complete. We found in FreeBSD, I ported it to FreeBSD 11.2 as a proof of concept, and Maxime implemented fully in NetBSD current. And this is like, those are more than 20 leaks from everywhere, from dynamic memory, from the kernel stack. Some of them are bigger, like 900 bytes, 92. Some of them are smaller. Usually those are half of a pointer on AMD64, what we found. And the research basically goes on. Those are the direct results that we found by using KLEAK. So I was told there will be soon a security advisory by NetBSD about many leaks, more than 15, 16. I don't know what happened to the FreeBSD leaks. They were fixed all, but there's no security advisory so far. I don't know. What happened was, this was kind of a cool, like a follow-up by the FreeBSD devs. The leaks were reported, and what they did basically, they looked around in the code. Where one leak is, there may be another. So on the left-hand side, there was one leak in getDir entries, and they found out that were like 20 implementations of file systems there was a leak, and they fixed them all. So as a follow-up, they fixed like 50 or 60 more kernel memory disclosures, which was great work. Yes, so as a conclusion, so we saw what are kernel memory disclosures, so what they are, how to avoid them. I presented you our approach, which is called KLEAK, which is fully implemented in NetBSD, and it detected more than 20 of those memory disclosures, and as a follow-up, dozens of those were fixed by other developers. And so it's a thing. The one more thing is the BSD are far from being KMD free. That's true for other operating systems as well. So instead of planting a tree, maybe we can fix a memory disclosure, and we're getting closer to a full secure system. So keep looking for them, and thank you for your attention. Any questions? Yes.
How expensive would it be to zero at compile time, like have the compiler insert zero instructions for the stack that's used by kernel functions?
Excuse me, you?
Could the compiler insert zero instructions could you modify the compiler to at function entry zero out all the stack variables, essentially modifying the C language?
Actually, there are some projects, and like for example on Linux, there's something like that. Every time you enter into a system call, it will zero out your stack. So then there's the issue performance. So those are like, I don't know how many CPU cycles, but if it's performance critical, you won't need it. You don't want to have it. But it's not a standard thing. It's one of those security patches. I don't know how they're called, like the Linux security patches maybe. Yeah, but then again, for example, there are leaks that are from because you wrote it there, and then there are leaks, for example, inadvertently. Then there are leaks from the heap. So then you have to patch your heap implementation as well. So there are many places where those leaks can and could occur. So, yes.
What do you use as a key for the heat map?
As a key.
Yeah, how do you identify the entries?
So this was actually, I'm not the heat map. Was the greatest idea of Maxime, who implemented it. So asked him. That was so I cannot give you the details on the heat map. Thank you.
Thank you.